OK. Open your desired model, first in menu bar, Tools, Material, Assign Material, in dialog box. Choose Steel Material from list, and then apply the command, OK. It's very good. Back again and in File, All Application, Simulation, Design Simulation, in FEM and Simulation dialog box. Keep the default parameters, apply an OK and finish it, then OK the solution dialog box. And accept all of its options. Very good. Now in Simulation Environment, first in Ribbon Bar. Find and run the pinned constraint, OK. And in dialog box, select cylindrical face of hole, very good. Do it and complete the selection and then OK the command. Then find and run the slider constraint in Ribbon Bar. Click and run the command and in dialog box, in Planar Object, select this two-planar face. Select it inside of the piston, find it and complete the selection, OK. It's very good. In sliding direction, select Z direction negative. Do it carefully and finish the job. It's very good. Change the type to rigid. Apply the command, OK. Again make a new region in Simulation Navigator, and in dialog box, name is Pin 2, in Region Object. Select cylindrical face of connecting rod, type is rigid, and apply the command and finish it. OK. CFD analysis in Siemens NX software, Computation Fluid Dynamics. We have a 3D model. OK. Click File, New. Find the Simulation tab. In the list, find the Center Thermal and Flow. Note that its type must be FEM. OK the dialog box. Now in Graphic Window, rotate the model and check it out all of 4 outlets, and its figures. OK. It's very good. Then exit from dialog box, and now the flow simulation is ready to solve. In this video tutorial we want to solving a thermal analysis. We have a 3D part in Graphic Window. In File, All Application, Simulation, Design Simulation, enter the simulation environment, very good. In New FEM and Simulation dialog box, change the analysis type to Thermal. Apply and OK. It's very good. Then in Solution dialog box, again check the analysis type. It must be Thermal. Apply, OK. First step is Material. In Ribbon Bar, Constraint Type, find and run the Temperature command. Select back edge of big part. And write 20 degrees. Try to do it and complete the job. Apply and OK the command.
In this video tutorial we want to start the FEM simulation process in Generative Structural Analysis Workbench. Now in Part Design Workbench we have this 3D body. First step is assign material, find the command here. But first click and select the current body in Design Tree and then run the command. Now in Library. Default Material Catalog, there are many different materials category tabs: construction, fabrics, metal, stone and wood, and etc. In Metal tab, select steel from list and then click Apply Material. OK. For example, select this top flat face. See its red symbols in graphic window, translation and rotation. There are 3 translation degrees of freedom per node for each element, and 3 rotation degrees of freedom too. This command allowing you to fix any combination of available degrees of freedom. Write your desired value about x-axis, y-axis and z. And each time check it out in graphic window. OK. See its red arrow symbols and then test the different values more and more. Do it and complete the job. First command is deformation. Find it and run the command and then check the model in graphic window. See the deformation of body in graphic window and check it out carefully. Do it and complete the job. Good. Now in Analysis Tools, find and run the Animate command and then, you can see its animation. OK. You can increase the step numbers and then check it out again and test the model in graphic window. OK.
OK. Simulation in PTC Creo software. Simulation lets you examine how your model will behave in the real world. First in Ribbon, click on Application tab, find and run the Simulate, and enter to the Structure Simulation mode. Here, the first step is defining material. In Ribbon, Materials, click Material Assignment, and in Material dialog box, in Material Directory, in List, Legacy Materials, and Standard Materials, for example in Standard Materials, and Metal, for example select Cast Iron Malleable, double-click and then OK. Again OK. The Material Assignment dialog box. OK. Now in graphic window you can see the icon of Material Assignment. Next step is Constraints. In Ribbon, here, Displacement Constraint, Planar Constraint, Pin, Ball and Symmetry Constraint. OK. Here you must specify the pressure values, change the unit to megapascal, and value is 500, OK, it's so good. Now click on Preview icon, and see it in graphic window. You can see this purple arrows in your direction, OK, so good. Again in Ribbon, Run. Click on Analysis and Studies command. Now in Dialog box, in File, New Static, and OK. In the new dialog box, check the loads and constraints in List. Try to do it and complete the job. We have one constraint, and one force, then OK the dialog box. And back again to Analysis and Design Studies dialog box. Now click on this green flag, Start Run. Now in Simulate Result Environment, in Home tab, you can see the stress in von Mises, and this colored column, and you can see the von Mises stress value in different sections of part. You can change it to displacement and magnitude. OK, see the changes on model. In View tab, click on Continuous Tone to see better the results.
In this video tutorial we want to explain the Solidworks simulation plugins. If you have installed Solidworks completely, the Solidworks simulation will be available to you. OK. In the Command Manager, Solidworks Add-ins tab, click on Solidworks Simulation. Again in the Command Manager, the Simulation tab is added. Click on it, and click on New Study icon. As you see, the Study dialog box is appeared. In the General Simulation, for Start a Static Analysis, Finite Element Method, click on it, and then OK the command. That's very good. The static new design tree is appeared. OK. That's very good. First of all, you must specify the material of component or assembly. To do this, right-click on the model and click on Apply/Edit Material. The Material dialog box is opened. In the Solidworks DIN Materials or Solidworks Materials, find your desired material and choose it, so you can see the green arrows again. Or point. Delete the edge and this time select a vertex, and see their green arrows. And in Advanced Fixtures, the first is Symmetry, suitable for mirrored components that's shown in the figure. By selecting the fixture area, the software supposedly completes the other half of the piece. Next is Cyclic Symmetry, suitable for circular patterned components, that's shown in the figure. And enter the sketch environment. Draw a circle and no need to dimensions or relations. Diameter is 25 millimeters. And OK the sketch. In Insert menu, Curve, Split Line, Projected Radio button. Select the sketch. And then select the desired flat face. Change the direction if needed. And do it. OK. Finish it. Then right-click on the external loads and select the remote loads. OK. In the type, select Load, Direct Transfer. In the blue box, select the splitted circle face. And in the location, my desired load is acted on the shaft with 25 millimeters O diameter. Now you can see the deformation scale in this area. In this location you can see the von Mises stress in color separation. And you can see the yield strength value. Right-click on Stress 1. And click Animate. Then you can see the reaction of component by animation. Decrease the speed of animation with help of this slider.
Okay, now in this video tutorial we want to explain the thermal analysis in Solidworks simulation add-ins. In assembly environment we have this two parts. Now waiting for complete the solving problem. And then results is appeared. OK. You can see the temperature in Kelvin. And see it in color separation column. Right-click on Thermal 1 and select Chart option. See the maximum and minimum plot. Now we want to simulate the CFD, Computational Fluid Dynamics, with SolidWorks Flow Simulation. OK. We have an assembly that's created from 4 separated components. This is ball valve skin. And other 3 components are caps. That's sealing the valve skin holes. Again, right-click and edit definition. Change the number of spheres to 50. And OK the command. Now you can analyze the simulation in better situation. As you see in the colored column, the spheres with cold colors move faster than the warm color ones.
OK, stress analysis in Autodesk Inventor software. We have a 3D model here, now an Environments tab. Click on Stress Analysis icon, and now you are in Analysis Environment. First, click on Create Study command. And in dialog box, keep the static analysis type and OK the command. Now in Analysis Environment, in Ribbon. Check the study tree. First step is Assign Material. Find it in Ribbon, Material, Assign Material command, OK. In dialog box, click on Materials icon, or in this list, find select the steel, and complete the job, and finish the command. In Ribbon click on Mesh View icon, and see the automatic Smart Mesh on your component. Now in Ribbon, find and run the Local Mesh Control command, and in dialog box, you can select your desired face or edge, and change its element size, or mesh size, and write your desired value here. Test it yourself later. OK. By default you can see the von Mises stress analysis result. Unit is megapascal. Check this color bar. And you can see the von Mises stress value in this area, and check it out on your 3D model. Click on Convergence Plot, and see it completely and check it out carefully in Graphic window. Now in Ribbon, Maximum value and minimum value. Run this commands and check its operation. So good. Find the maximum von Mises stress value in Graphic window. It's here, and do it for minimum value. OK.